Okay.
So, this is worrying because they estimate that you have to vaccinate like 80% of people to get the herd immunity, and if only 70% wants to be vaccinated, then maybe we will have to force people to get vaccination, and this will be like...
How can you force 15% people? It's not a one person so that you can force, then you can bribe them or something you can do.
Yeah, I think that there will be bribes in a sense like, if you're vaccinated, you can go to cinema. If you're not vaccinated, you cannot go to cinema, you cannot travel, you cannot... Maybe this will work somehow.
At least people say you cannot travel any flight and train. That's also enough. I mean, that.
Yeah.
But it is very hard to, I mean, for 15% people is there, then they have huge support. So it is very hard to implement that kind of propaganda.
If they try to do this, there will be like huge protest riots and stuff.
And that will spread the corona again. This protest, yes. But I saw yesterday the number is significantly reduced. Yesterday around 300 or something the active cases were there.
Yes, so we have the best situation since a year. It's like the pandemic is almost gone, but unfortunately it's... it looks like it may come back. I'm sorry, I have an urgent phone call. I will just tell them that I'm busy. Okay?
Professor Paningray?
Dzień dobry.
There?
Dzień dobry, ja mam teraz jestem na konferencji, więc bardzo proszę o szybką wiadomość. Jak sytuacja wygląda?
Sir.
Yeah.
So people are लोग धीरे-धीरे आ रहे हैं. अभी तो actually वो सेशन थोड़ा लेट चला ना, लोगों को तो लंच भी करना पड़ेगा.
Yes. Dr. Pawłowski will take a few minutes more, 4-5 minutes more.
Yeah, I'll tell him. Yeah.
Hey, sorry about this.
It's fine. Marcin is meet Professor Paningray, and who is the convener and the main organizer. Yeah.
It's nice to meet you.
Same here.
You have a common connection, Devasis Saha.
Devasis Saha, correct.
Oh, yeah, my favorite student.
So he is back here in Kolkata.
Yeah, he is not.
Yeah.
You have a very nice background. Is that moon?
I'm sorry?
Yes, this is moon, and it's not software, it's hardware. So this is actually my wallpaper in my office.
Okay.
You should visit us sometimes when things improve. We will definitely would like to have you here with us.
Thank you. I would be very happy to.
How many times you came to India? I mean, for conference. You know, I know you.
3 times. I think I've been 2 times in Patna and once in Bangalore.
Okay.
Plus, I've been a tourist once.
Yeah, you spent a lot of time in Varanasi, right?
Yes. I really liked it there.
If I remember correctly, you bought some musical instrument from there, right?
Not a musical instrument. It was some rugs and cushions and so on. Okay. My story with Varanasi is that there was a musical instrument in my bus playing so loud that I got almost deaf, and I was. And in the end, I couldn't even walk because I was so dizzy from this noise. But this was very long time ago. 20 years now.
So Marcin will start a little bit late, 2-3 minutes late, because the last speaker was, it was little delayed. So the students there went for lunch and they are coming slowly. Yeah. We'll wait for 2-3 minutes.
Okay, I'll wait. No problem.
And just to tell you that in the Zoom platform, we'll have not much participant, maybe around 100 or something. But we have a huge number of registered students, and they will be in the YouTube channel because we could not give the access to the Zoom platform to everyone. And the questions, you can directly take it from here, or I can read it for you. And the YouTube channels, I shall read from there. Sorry.
Yes, so I'm fine with every option, but
okay.
So, and also, if there are questions during the talk, I'm fine with stopping and answering them in the middle.
Sure.
Participant. The 17.
So this center, International Center for the Theory of Quantum Technology, is the same building you have, right? Where I visited.
So when you visited, we were about to move. So I'm not sure if you visited the old thing or the new thing. So
no, I think the old thing.
The old thing. Oh, this is very sad. Unfortunately, our university sold this building, and now we have this modern building. It's much worse. I don't like it at all. So I really like this old villa.
Yeah, the old villa was very nice. Yeah.
It was pretty cool, but now not because at this time our university had buildings all over the city, and they decided to sell all of them that are not on the campus, and for the money they got, they built new buildings on the campus. So now everything is on the campus, and we are also there. But it was much better in the villa.
So there is no center in the Sopot now. All are in Gdańsk.
No. It's all moved to Gdańsk.
So then you have to go to the Gdańsk every day.
Well, I had to, but then the pandemic started, so I'm right talking from my home right now.
Okay.
We have around 60. We can just slowly start.
Okay.
So let's just start by introducing Marcin. Okay. So formally, good afternoon to the participants and good afternoon to Professor Marcin Pawłowski. It is our great pleasure to have him, Marcin, with us today. And we are really thankful to him because he agreed to give this lecture. Marcin is currently a professor at the International Center of the Theory of Quantum Technologies in the University of Gdańsk. And he is the head of the Quantum Cybersecurity and Communication Group at that center. He did his PhD in 2010 from Gdańsk University, the same university he now belongs, and did postdocs from the Bristol University, UK, and he up to 2010 to 2013, and he has joined as a permanent faculty member at Gdańsk University in 2013. As you know, that Marcin is one of the very few young researchers who have wide impact and recognition in the field of quantum foundation and quantum information theory, and he is actually quite renowned in the field of research and has made quite a number of important and pioneering contributions. In fact, during his PhD, he had published a Nature paper on information causality as a physical principle, and I think that earned him a wide recognition in the field. And after that, he continued publishing such many important works. Up to now, he has published around 120 research articles in high impact factor journals, including Nature, Science, Advanced Science, and PRLs, many PRLs. And in fact, he published a very interesting paper in the last month in the PRL. I think he will be talking about that paper also.
A little.
Okay. He's also, interestingly, he is the founder of a startup company, it's a Secure Spa. and it's a random number generation company, and maybe he may say something about it later on. So it is our great opportunity to listen to him today, and he will be talking about the information theoretic principles of quantum theory. And it is a very interesting and important topic. So I request the students to listen to him and ask questions either in the chat box in the Zoom platform or in the YouTube channel. So with this, I'd like to invite Marcin to deliver his lecture.
Thank you, Alok, for this nice introduction, and most of all, thank you for inviting me to present at this conference. Now I will share my screen and start the presentation.
Yeah.
Is it working?
Yes.
Okay, great.
It's perfect.
So I will talk about information theoretical principles of quantum mechanics, and as Alok said, my group is working on quantum cybersecurity, which is a very practical thing, and I also have a company which is doing practical, tangible devices, but part of my interests are really foundations, even philosophical aspects of quantum mechanics, and this is what this talk is going to be about. So what are principles? The most important thing about principles is what they are not. They are not laws. Laws are observed and somehow derived, and principles are assumed. So you don't need a proof to have a principle. You just say, okay, I believe this thing should happen in the world. The universe should adhere to these particular rules because this makes sense, and you don't have to prove it. You have to argue why it should make sense. And the best example of a principle is the principle by Leibniz of the excluded middle, in Latin tertium non datur. So it's a basic principle of logic. It says either something is true or is false. There is no third option. And this is very reasonable principle, but still it's a principle. Nobody proved it, and as with many principles, they can be challenged. There are some ideas, there are some different versions of logic which allow for the third option, but for most of the purposes, for most of the time, most people assume that this makes sense and we should adhere to it. So in cosmology, or I'm talking about cosmology because this is a part of physics where the principles are most prominent and most easy to understand. We have a few very important ones. So, for example, mediocrity principle. It says that if you have a collection of objects and you pick up one at random, you're most likely to get something which is representative. So why do we use it in cosmology? Because we're interested to know why our universe looks like it does, and people are saying, okay, if there's a multiverse, an infinity of universes, and we pick up one, and this is ours, we shouldn't get something highly unusual. We should get something which is mediocre. And this is what this principle says. It makes sense. Another is cosmological principle. It basically says that the distribution of mass across the universe is uniform if you take the scale big enough. And this is another interesting principle, because this one is heavily debated. People are finding more and more examples where this mass is not distributed at the in a uniform way. But then if you then raise the scale to be big enough, it comes back. Or also if you add time to the equation, then it starts making sense. And this principle goes in pair with relativity principle. So this one I'm sure you know very well. It was first formulated by Einstein, and it basically says that the laws of physics should be the same regardless of the frame of reference. And this goes, as I said, this goes really well with the previous one, because the previous one said that mass should be distributed more or less evenly. So relativity principle says that laws should be the same everywhere. And cosmological principle says that not only laws, but the conditions are more or less the same everywhere. So those two together mean that the universe is more or less the same everywhere. And the most, I think, interesting of the principles is in cosmology is the anthropic principle. It's so interesting that actually philosopher Bollström counted more than 30 versions of it, but it comes in two flavors. One is so-called weak anthropic principle. It says that we are in a part of multiverse in which we can exist. So this principle is supposed to answer the question why our universe is like it is. And the answer goes like this. Okay, if it was different, we wouldn't exist. So we take an infinite set of the multiverses, of the universes in the multiverse, and we end up in one in which we can exist. But there is a stronger version, and the strong version of the anthropic principle says universe can exist only if it's observed. So it's the argument goes like this: if the universe isn't observed, it doesn't exist. So it must behave in such a way that it allows for observers to exist. So these are the most important principles in cosmology, and I presented them mostly for you to get a feel what principles really are. So you don't prove them, you just assume they are correct, and from them you get you get to derive some properties of the universe. But nothing really forces us to make a claim that all the principles that we have are actually true. This is not the case, and at the 100 years ago, many people really doubted the relativity principle, and currently the cosmological principle is also heavily debated. Now, one of the most important principles that we have is locality principle, and it can be traced back to Newton, who wrote this long text in which he basically says that he doesn't believe that gravity can be mediated between objects which are far apart without any actor in the middle. So if Earth and Moon are connected by gravity, there must be some particles, objects, or immaterial agents which work to transfer this force or action. And Einstein had a very similar thing to say, because he claimed that there is no such thing as spooky action at a distance. And this is, although he wasn't talking about gravity, but entanglement here, it was more or less the same. If I have an object here and another object somewhere else, it's inconceivable that that one of them acts on the other at a very large distance without anything actually passing between them. And as we know, when Einstein said it, he was in opposition to the quantum theory, and now a lot of people say that he was actually wrong. So I'm going to argue that it was not entirely the case. Both Newton and Einstein, they were really smart people, and actually what happened was a small misunderstanding. So Bell took the feeling from Newton and Einstein, and who said that there is no cause without mediator. So basically what they were saying should be called local causality, meaning that if there is a cause, it must happen at the same location. If there are different locations and things in one location cause effects in the other location, there must be something that goes from one place to the other. And Bell derived a mathematical condition. He wanted to make it more precise, so that we could use experiments to test it. And this is what's Bell's condition. So basically, this E is called a correlation function, and C is here are so-called hidden variables. So what Bell is trying to express here is that he's saying, okay, if we have two separate places, in one there is a lab of Alice, A, and the other is the lab of Bob, B, then the effects on Alice's side can only depend on her inputs, lowercase a, and some hidden variables. They are usually denoted lambda, but I used C here because of reasons which will be evident soon. Anyway, so he took Newton's and Einstein's ideas and made them something else, which allowed him to formulate it more rigorously, but at the price of slightly distorting the initial idea. And then the ideas of Newton and Einstein were much along what is called Reichenbach's principle. So Reichenbach in the 1940s wrote a very simple principle, and it makes a lot of sense. It says if A and B are correlated, then either A causes B, or B causes A, or they have a common cause. called C, and this is why here I put C as a hidden variable. This was the meaning of hidden variables in Bell's cases. And if you look at it, you may think, okay, Bell's locality makes really sense, because if A, the outcomes at Alice's lab are can only be caused locally, and this is local causality, then they should be a function of only things local to Alice, A, and some common cause of A and B. But this might not be that easy. So as you know, the Bell condition of locality is a source of Bell inequalities, and the most famous one is CHSH. And I'm sure you know CHSH, but since I'm talking about principles, I wanted to show you one of the coolest derivations of it. So what I'm doing is I'm using a painting by M.C. Escher. It's a very famous painting of, or actually a drawing of infinite stairs. If you look closely, you will see that there are two rows of people, and the inner one is always going down, while the outer one is always going up on the same stairs. Such stairs shouldn't exist in any universe, but we can imagine them, we can draw them. And if you assign the height of the points A0, A1, B0, and B1 to the stairs, we can say that in any reasonable universe, the upper condition on the right-hand side should be should not be fulfilled. So basically, if A0 is greater than B0, which is in turn greater than A1, which is then greater than B1, then B1 cannot be greater or equal A0. It simply is impossible. And now, if you assign the probabilities to these heights being different happening, we know that at least one of them cannot happen, and also not all of them can be false at the same time. This represents the impossibility of stairs always going down or up. So these two next inequalities reflect exactly this, and actually you could stop here, because these equalities are already a version of so-called CGLM-P inequality, which was presented by Zoran and Gill in the 90s. So these are already Bell inequalities, and since they are a generalization of CHSH, from them it's very easy to derive CHSH inequality, which I do in 2 lines, and we have it here. So basically, what CHSH inequality tells us is that stairs like Escher's shouldn't exist. And what quantum mechanics says that, well, they can in our strange quantum world. But why I'm talking about this? Because, look, if you think about this, what happens if Bell inequality is violated? If Alice's input is 0, she wants her output to be equals to Bob. If Alice's input is 1, she wants her output to be equal to Bob's output XORed with his input. So in other words, if A is equal to, okay, I'm sorry. the way I wrote the inequality here, it should be Bob. But so look, if Bob input is 0, so his output is going to be B0, and he wants it to be equal to A0 or A1. It doesn't matter. It increases the probability here. But if Bob input is 1, then he wants to be equal to Alice only if she has input 1, and something different if she has input 0. And this means that basically if Bob has input 1 and Alice changes her input at the other side of the universe without changing her output, then Bob gets to know Alice's input without any communication. And this was the basis of so-called flash device, which was patented by Nick Herbert in late 70s or early 80s, if I remember correctly. And actually, many people later had this idea. This is called so-called Bell's telephone. So it's a way to use Bell's inequalities for instantaneous communication. And we know that communication shouldn't be instantaneous because this violates relativity principle, but also it violates local causality because communication leads to a cause. So imagine that somebody is going to transfer me from the other side of the universe important message. I might act differently depending on the message that I obtain. So I'm patiently waiting for this message to come. And then when it comes, it changes my behavior. So it causes something. So this would violate local causality. And this is the probably most important slide. And there's nothing new here, just a recap what I already said is that if we have a probability distribution which with high probability has this condition fulfilled, so the outcomes of Alice and Bob XORed are equal to the product of their inputs, they can violate CHSH inequality, and this can be used to make a change in the other lab without any communication. And the input of Popescu and Rolich in the 90s was that not every change implies information. There might be changes that do not give us any information, so they are not causing anything. If I have some information about what just happened in the other lab, I can change my behavior and this really costs something. But if something changed in me, but I have no idea, no way to actually detect this change, it means this change didn't make any cause. And this is how the collapse of the quantum state works. If somebody on the other side of the universe measures a part of entangled state, it causes a collapse of the state here in my lab, but I don't know anything about it. What changed is the knowledge of somebody else about me, not my knowledge at all. So So quantum correlations should not be used, cannot be used to send information, and this is the basic of the most important principle probably in quantum mechanics, the no signaling principle. And Popescu and Rolich did more. So they explained why the device of Nick Herbert here, why this device would not work. And this is through randomness. So basically, what happens is that you cannot send any information via this telephone if the outcomes of measurements on entangled state are intrinsically random. And here I have a plot from a paper by Pironio and the others from 2010, where they actually make this statement quantitative. On the x-axis is the violation of Bell inequality, and it shows, and the most important line here is C, the blue one. It shows how much random the outcomes of the experiments have to be in order for a theory to violate CHSH inequality and not violate no signaling principle. In other words, you need to have some randomness which somehow clouds the changes of your system in order for Bell inequalities to be violated, but not sending any information and therefore not making any cause. So in other words, and the way that I think we should really understand no signaling principle, it means that information requires a carrier. Some people relate no signaling principle to the speed of light, but I think that this is not the most important thing here. So light is one of the carriers, but if we have just two devices which are close to each other and could in principle send information, but are not sending them, and we can just assume that they are not communicating, this also follows no signaling principle. So basically the locality loophole in the Bell inequalities is not that important. Okay, another principle which is required to derive Bell inequalities is free will principle, which in my opinion should be called statistical independence. And this is quite simple. It means that basically the system that violates Bell inequality should not depend on the inputs. So we might imagine a super deterministic universe in which the initial conditions of the universe decided what the inputs we will choose to our device, and if this happens, of course, any probability distribution is allowed because it was already decided at the beginning of the universe, and there is nothing that we can use to disprove it. So we have another principle for it, statistical independence principle, which says that, okay, maybe universe is super deterministic, but even if it is, it's not maliciously super deterministic. So it's not trying to trick us into looking that it is random while and non-local, while in fact it is local and deterministic. So now recap. So what do we have until now? So we see that local causality actually is a root of no signaling principle. If you think about this, they have basically the same meaning. Local causality says that that any cause can be transferred only by some medium, and no signaling basically says that no information can be carried without a medium. So if you then say, okay, a cause is a flow of information, then these two things become basically the same. And the only difference is that along the way from reasoning of Newton to Popescu and Rolich came Bell and wanted to make the condition of locality more mathematically rigorous, and he did it, but by adding some extra constraints. So you should be careful not to confuse Bell's locality with local causality. And before I go further, I wanted to mention a cheesecake machine from one of the Douglas Adams' book about, from the Hitchhiker's Guide to the Galaxy series. It's a machine which works according to the rules of classical physics. It has a cheesecake. It can be actually any object, but this is a funny book, so Douglas Adams chose a cheesecake. And since every particle in the universe is acting instantaneously on and producing some force, say gravity, on every particle of the cheesecake, if you measure the cheesecake precisely enough, you will know the whole universe. And this, there is some important message to learn here, because if we assume that there is some signaling in the universe, the relativity theory doesn't immediately break down, because you can save it by assuming that there exists a preferred frame of reference. There are some theories. For example, here I have a Bohmian description of double Stern-Gerlach experiment. In this experiment, changing the field in one of the labs actually changes the outcome at the other. There's instantaneous signaling, and we don't see it because we don't know the initial conditions of the particles. But if in Bohmian mechanics somebody had access to the initial conditions and knew the position of the particles, then this theory could be used to signal, but only between the two particles that are entangled. In the universe where cheesecake machine exists, there is instantaneous signaling between every possible particle in the universe. So actually, the rest of my talk will be devoted to different refinements of no signaling principle, and this cheesecake machine is this cheesecake machine is one of them, and this is a refinement of the no signaling principle in one way, making it weaker. So basically, if I say there is no cheesecake machine, it means it's inconceivable that every particle in the universe sends information to every other. But it doesn't mean that there do not exist pairs of particles which communicate. So this is a weaker version of no signaling, but then there are some stronger versions of no signaling, and this is the rest of the talk, and the rest of the talk will be devoted to them. There are 4 that I would like to talk about. macroscopic locality, non-trivial communication complexity, information causality, and local orthogonality. All of them were proposed quite recently, at least when you compare it to Newton and Einstein. So, macroscopic locality. Here you have a graph that we really like to draw when we talk about foundations of quantum mechanics. So these are sets of allowed probability distribution. The smallest one, the small square, is locally realistic. So this is these are classical probability distributions which are bounded by Bell inequalities. The biggest set is no signaling, and the circle in the middle is quantum mechanics. And already from this you see that no signaling principle doesn't signal quantum mechanics. It doesn't single out quantum mechanics. And let me go back to this slide. So what you see here is that, what I wanted to point out here is that no signaling allows this probability distribution here to exist even with E and P equal to 1, while quantum mechanics only allows for E to for probability distributions to exist with E smaller or equal 0.707. And actually, one of the driving reasons behind all these new principles, which are generalizations of no signaling, was to find a principle which singles out this value. And we were successful in more than one way here. So macroscopic locality is one of these principles. It basically says, okay, it's fine if you violate Bell's inequality, but only on a microscopic level. If now you have many independent entangled particles and you want then you can measure them at each lab and obtain a macroscopic Bell experiment, and you could observe the violation of Bell inequality in our macroscopic world. This would be very, very cool, but macroscopic locality says that this is impossible, and the noise that we would observe, which comes basically from randomness of the results, would cloud everything, and we would not be able to violate Bell inequalities in the macroscopic world. And this was a really nice idea by Miguel Navasquez and Harald von Derlich, who were able to show that from this principle only, you can derive exactly the classical bound on CHSH inequality. And the relation between no signaling and macroscopic locality principles is not so straightforward. You might think about it like this. Look, I have this device, and in this part B, detector B, receiver, you see this element called neutral beam splitter. So if we have high intensity beam of many particles and it goes to this neutral beam splitter, then half goes up, half goes through, and then you can measure these particles in two different bases. So Bob would know at the same time what his measurement with setting 0 and 1 would be, and he could get Alice's result. So in this sense, macroscopic locality really seems to flow directly from no signaling, but there is a tiny assumption here that this splitting at this neutral beam splitter can really happen and not mess all the things. So this is a natural assumption, and if we make it, then macroscopic locality really is a generalization of no signaling. But if we don't make this assumption and look only on the mathematical formulation of macroscopic locality, then it is not related to no signaling. And in most of the work when we work in with macroscopic locality, we have to impose no signaling independently. Then there is a principle of non-trivial communication complexity. It was discovered by Wim van Dam, and this is very beautiful. So he found out a very simple protocol, which I have here on this picture, which allows Alice, the sender, to take 2 bits, encode it in a single bit message, and send it to Bob. Bob cannot decode both of them, but if he has PR box, PR box means Popescu-Rolich box by the authors of that paper that I mentioned, and it's a box which gives success probability 1 to this thing in blue occurring. So the outcomes of Alice and Bob are, their XOR is always equal to the product of their inputs. Now, if they have this box and use Wim van Dam's protocol, Bob can always, with certainty, gets exactly 1 of Alice's bit, and he chooses which one. And then Van Dam goes further and says, hey, but then you can concatenate the procedure, which means that if you have more boxes, then you can take 2 additional boxes, encode 4 bits into 2 messages, and then use a 3rd box to encode these messages in a single message and send to Bob. And you can repeat this concatenation procedure many times, and what you can do is you can send exactly 1 bit of information to Bob. Bob will be able to get exactly 1 bit, so nothing looks wrong here so far, but he can choose which of the bits of Alice it will be. And this is really strange because it looks like a compression procedure where Alice compresses the information, and it's a lossy compression. So out of million bits, you have only 1 bit of information, and then Bob decompresses it and gets exactly 1 bit, but it is Bob, the receiver, who chooses which bits are lost by Alice in her compression. So he works somehow backwards in time. And Wim van Dam didn't use this argument. He used a different one. Look, if Alice and Bob want to compute any function, Alice, who knows X, her input, she can prepare a message which will be the outcome of the whole computation for different values of Y. And then she encodes all these outcomes, possible outcomes, using this protocol, and sends to Bob, so Bob gets it. And now you see why it is strange, because with only 1 bit of communication, Alice and Bob can compute in a distributed way any possible function. And this sounds really impossible. Our universe shouldn't allow for this. So this is why Wim van Dam claimed that PR boxes should not exist. And later, Brassard and others used clever non-local error correction and showed that if E in this formula above is greater than 0.816, you can actually first improve the quality of your boxes to arbitrarily close to 1, then use Wim van Dam's protocol and compute every function. So, and this is very nice principle because we believe that in our universe, it shouldn't be possible to compress information like this. And this is what I just said. And the next principle is information causality. It's very similar to the previous one. So, so if you look at the protocol of Van Dam, you can say, at some point, when Alice already sent 1 bit of information to Bob, then whole, and then we can totally forget about her, and the whole information is at Bob's side. Now, this information shouldn't be more than was sent to her. So if Alice sent only m classical bits to Bob, Bob shouldn't have access to more than m bits of information. And now it doesn't matter if he can access only 1 bit at a time. If he can potentially access more than m bits of information, then something must be wrong. And actually, information causality can be derived, this formula, this inequality here can be derived from basic principles of information processing, including no signaling. So you can see directly that information causality is a generalization of no signaling by adding some other things. And why I like this principle is not only that I was involved in its discovery, but also because it says that it should hold in any universe where very basic properties of information processing are true. So it's very like anthropic principles, which say, okay, the universe is like what it is because it has to be observed. And observation is nothing more than gathering information and processing it. So information causality is similar in this way that it says, okay, if in the universe are any observers capable of processing information in a sensible way, then this principle should hold. And as I said, that it's a generalization of no signaling, but when n, the number of bits, goes to 0, then you can show that information causality actually goes to no signaling. And its relation to non-trivial communication complexity is that basically non-trivial communication complexity says it shouldn't be possible to compute easily any function, while information causality says it shouldn't be possible to easily compute a particular function. And this particular function is basically guessing some of the bits of the center. And I'm slowly running out of time, so I'll try to be brief. The relation of information causality to macroscopic locality is that information causality is stronger. So some some reasons, some points were already shown in 2010, where so these were so Cavalcanti and others have found probability distributions which violate information causality but do not violate macroscopic locality, and together with my coworkers this year we put a paper on the archive where we showed that in this particular scenario no macroscopic information causality is at least as strong as macroscopic locality. So we know that information causality is much stronger than macroscopic locality. And the last principle that I want to talk about is local orthogonality. It's extremely cool in a sense that it's obvious that it must hold in every universe. So imagine that we have two events which are mutually exclusive. So there's a set of parties, they have different inputs, and one of the parties has different outcomes. Then it's obvious from actually Leibniz principle tertium non datur that both of them cannot happen at the same time. So if you add the probabilities of them happening, this probability should be smaller or equal 1. And actually, this thing is enough to prove some nice results, including the maximal violation of CHSH inequality. And its relation with no signaling, it's really interesting. Because if there are only two parties, you can show that these are equal. But then, what you can do is you can take many copies of the PR boxes and do something different than people from information causality and Van Damme did. What we did was give divide each box into two parts, and one parts all go to Alice, the other parts go to Bob. And here, what they do is they can take, for example, two PR boxes and say, okay, now we have 4 parties. And this is a different scenario in which local orthogonality is stronger than no signaling. So, and actually stronger than information causality. So what you see here in this bottom drawing is a slide from this paper where information causality, the blue line, and local orthogonality predictions are shown, and you see that in this zoom in, they really cross each other. So actually, not only local orthogonality allows you to derive the Tyrrellson bound, so the bound on the maximal violation of CHSH inequality, but it also is stronger than information causality. And this is funny thing because it's a principle which is as strong as no signaling with 2 parties, but with clever use of 4 parties, you can draw conclusions about 2 parties which are quite strong. I really like this one. And now there is this thing called almost quantum. It's not a principle at all, but it's a very powerful thing. So on the right-hand side, you see some sets, and this is a picture from a paper that I have down here. It's about so-called NPA hierarchy. It's basically a hierarchy of conditions which in the limit allows you to bound a quantum set. So Q here in the middle is the set of allowed quantum probability distributions, and Q1 corresponds to macroscopic locality. Now, Q almost quantum is sometimes called set Q1 plus AB, and it's a set which lies in between Q1 and Q2. And on this picture, it might look that it's really far from the quantum set, but you should really look at the picture on the left-hand side. You see already how close information causality and local orthogonality are close to the quantum set, which is this black solid line here. Q1 plus AB is even closer to the even closer to the quantum set, and it was proved by Miguel and his friends that almost quantum is strictly stronger than no signaling, local orthogonality, no non-trivial communication complexity, and macroscopic locality, and also information causality for more than two parties. So the only hope to beat this and be stronger is using information causality somehow for two parties. And we recently had a paper about this. We slightly modified our informational causality condition. The modification is in this formula on the left-hand side, and instead of the number of classical bits transferred, we now talk about the communication of the capacity channel. So basically, we say that if I'm using a communication channel with capacity C, then Bob's information should not be greater than C. And we already formulated information causality like this. Actually, we thought about it like this from the beginning and explicitly formulated it in this paper from 2016. But now we were able to use it and basically get rid of the concatenation procedure, which was basically an artifact of Van Damme's approach, to rederive and make stronger all the results from information causality that we previously had. So now we have a new powerful tool, and we will be trying to use to prove that maybe information causality is stronger than almost quantum, which would make it even cooler principle. And that's all. Thank you for your attention.
Yeah, thank you very much, Marcin, for this. Yeah. Thank you very much, Marcin, for the beautiful and exciting talk. Let's see if there are a few questions.
I think I put too much information here. It should be 2 hours.
Yeah, there are many protocols are there. That's really interesting. And then let's see if there's a questions. Yeah. Okay, they say, I mean, question will come later on because people are, yeah. One question from Dipan is that, does the hidden variable in Bell locality imply local causality as information?
Could you repeat this?
Yes, sure. Does the hidden variable in Bell locality imply local causality?
No. These are so the problem with local causality is that this is formulated in a descriptive way as principles usually are, and Bell's is something very mathematical. So in order to be able to compare these two, we would have to formulate local causality in a mathematical way. And there are many different ways to do this. So if we choose a way to write it down in a mathematical way, we lose some meaning, and then some of them can be equivalent to Bell's locality. Some may be not, some may be stronger, some may be weaker. These things are incomparable. So if I may, I would also like to add that this some vagueness in principles may be actually a good thing, and this is somehow what differentiates them from laws of physics. So principles are vague and laws are concrete, but they shouldn't be too vague. So principles should allow us to derive laws which then can be tested.
Okay, thank you. And there are questions that it's a question from Ajay Semal. That is, in classical mechanics, we predict or compute a lot of information with just partial information. But in quantum mechanics, it is restricted very much. Why? It's a question from student. So you have to formulate the question first.
Yes. So I don't think quantum mechanics is restricting anything. If anything, it encompasses classical theory and adds different possibilities. But the thing is that the additional things which quantum theory allows us are actually very limited. This is why we don't have that much programs for quantum computer, and these limits are governed by a set of laws, principles, and so on, and very restricted. So this might seem that this is why quantum theory is more restrictive, but in fact it is not. So I'm not sure if I answered this question correctly. I answered how I understood this question.
Okay, thank you. What exactly, there's a question that is, what exactly the macroscopic locality assumptions? I mean, what are the similarities?
So macroscopic locality, the only assumption there is that you shouldn't be able to observe Bell inequalities violation on macroscopic scale. So, in more precise ways, if you have many different independent copies of entangled states, and you make measurements in Alice and Bob's lab, the deviations should be exactly like coming from random experiments. So you shouldn't observe one result more often than the other with probability greater than 1 over root n, where n is the number of entangled systems. And then you can make it even more precise, and this is what Miguel and others did in their paper on hierarchies, when they showed that macroscopic locality can be defined by positivity of some matrix. But as I said previously, the strength of principles is in them being a little vague and saying like general things. So I would stay in the initial formulation that I had. Basically, macroscopic locality tells you that you don't observe Bell violations on macroscopic level.
Okay. But what by that you mean that, like for example, you are doing this CHSH experiment that you mentioned many times. In such a case, instead of taking one singlet, you can take two singlet. In such a case, what happens? I mean,
so if I take two singlets, I would get some. So Mathematically, we know what happens, but if I want to stick to my definition, is I say macroscopic locality doesn't tell you about 2 singlets. It tells you about 1,000,000 singlets or 1,000,000,000 singlets. If you take billion singlets and make measurements, you don't observe any violation.
Okay.
So imagine this. For example, if you're violating a Bell inequality, then you have a source and it produces you entangled pairs, and they are being measured. And usually this happens very fast, and you produce 1 billion pairs per second. And if you are able to measure all of them, then you get billion of different runs of experiments per second, and you have a lot of data. But now imagine that you integrate your measurements over 1 second, and then what happens is that Bob says, okay, I got 500,000 outcomes 0 and 500,000 outcomes 1, and Alice says the same. And this basically tells them nothing. And what macroscopic locality says that the variations from this 500,000 should follow Gaussian distribution, basically.
Okay, in that sense. So I don't think there are many questions, but let me go to the YouTube.
Okay, in such a case, I will thank you for attention once again, and
now there are random questions, so I may ask a couple of random questions. That is, how to use quantum technology in cyber security? I mean, that are the questions from the students. Hello, Marcin? Hello. Hello. Was it Panik Dehi?
I'm sorry, I got disconnected. I'm back. So how to use quantum technologies in cybersecurity. This is really cool. This is what I'm doing. So basically, I think Arthur Eckert phrased this very, very well. He said, like, basically what EPR argument is all about is that if okay, maybe not. Maybe I will say it differently. So the best way is to realize that that violation of Bell inequalities implies randomness, and randomness at a very intrinsic sense. If I say something is random, it's not like a toss of a coin, a roll of the dice. No, it really says that there isn't any being in the universe able to predict the outcome of this measurement before it happens. And the cool thing is that it can mean an eavesdropper. So this is how I can produce random numbers. But it can also be used in quantum key distributions, because if I have an entangled state and I can prove by, say, Bell inequalities that nobody can guess these numbers, but it's a same number for Alice and Bob. So they get the same number, and we know that nobody else in the universe can get this. This is like a perfect security, and at least when it comes to cybersecurity, this is the root of every single protocol that we have. Okay, what I just said might be debatable, but I think it's possible to defend that Bell non-locality and randomness coming from it is the source of all evil and good in quantum technologies.
Thank you. Question from Janki. Can we prove causation?
Can we what?
Let me formulate it here. Why is correlation not a causation?
Because cause implies intention. So if for example I want to switch on the lights and I switch the lights, I caused them to be switched. But if I'm just sitting there and the lights switch without my intention, then there is no cause. I didn't cause them. So this is causation, and correlation is that two things happen together. So they might be caused by the same previous cause, or one might cause the other. But the fact that there exists this another choice that they may share a common cause means that correlation is not causation. And yes, I think.
Okay, thank you. There's a question from Soham that can we use the method of decoy photons in Bell experiment to find the number of photons stolen by Eve?
Well, decoy photons are usually used in prepare and measure scenarios, and I don't immediately see a way that they can be used in Bell experiments. But there is this saying that if an old professor says something is impossible, it might be well possible. So I wouldn't say it's impossible, but I don't see how one could do this.
So there are not many relevant questions. Students, you are here and someone you want to ask any question? The Zoom platform?
But already good number of questions. So
Yes. So I think I will thank you for your attention once again.
Very much.
It was my pleasure. Thanks for inviting me to speak again, and goodbye.
You. Yeah, goodbye.
Okay, thank you.
Very nice, huh?
Very nice, sir. Actually, this session is not that good one because 2 o'clock session is actually just after lunch, so people are not very. Just a half an hour and 45 minutes gap, so it was not very. Otherwise the topic was really interesting because it's a really interesting topic.
But I can also tell you, Alok, our Indian students in this correlation, causation, they are not really that.
Yeah. That's true.
Yeah.
But he's the talk was very nice.
That is true. Maybe some other time we can invite him once this thing gets over.
Yeah. He's a very down to earth person.
Very nice person.
Very good.
So so then these two will start our students.
Yeah, sure.
If you can attend, I will be